Our test next week would be on 7th of May. So today is 28th. Your test would be on 7th of May from 9 o'clock to 11 o'clock. And also it would be a combination of MATLAB and also hand calculation. So you have to know how to do MATLAB and also hand calculation. And let's say that if I ask you to show me the MATLAB, you have to copy all the codes that you have written in the M file and also the answer that you get when you run that particular M file. So you have to make sure that you include first the M file and also the answers that come out when you run that M file. So that's for MATLAB. For hand calculation, please make sure that you have graph with you, graph paper. So it must be hand calculation. Graph paper must be on a physical graph paper, not Excel. This is due to the fact that for your final exam, it would be graph, physical graph. So I would like you to have an experience on this. Otherwise, you will be shocked when you do your examination. Right. So I think we better start. Still 48. That's okay. We just start. Any question before that?
Doctor?
Yes.
How long will the test be?
2 hours.
Okay, thank you.
9 o'clock to 11 o'clock. Okay. Okay. So just wondering, the international students, do the international students have problem with this? Because I know that you have different time zone with Malaysia. Qasim? Anyone? International student? If your mic is not working, you can type in the box, in the chat box. Anyone? Okay. Qasim, who else? Musa, is it? No? Not here? That's okay. Okay, so we move on to slide, lecture number 6. Can you see the lecture slide? The slide now?
Yes, Doctor.
Okay, thank you. Right, so previously we have learned about mathematical or numerical integration. So we have Newton-Cotes integration, where we have trapezoidal rule, we have Simpson's 1/3 rule, Simpson's 3/8 rule, and so on. In this particular lecture, we are going to cover the ordinary differential equation. So in chemical engineering, we frequently encounter different equations. So for example, in thermodynamics, if you need to admit someone. So if you remember, if you refer back to your thermodynamics, I'm not really sure whether you have learned this, but in thermo we have Newton laws of motion. So this Newton law of motion is actually the second law of thermodynamics, where in this particular principle, what happened is that it's shown that the acceleration is what happened, right? Acceleration is actually equals to the differential of velocity with respect to time. So the rate of change of velocity is equals to the ratio of the force over mass, which in this case, this part here, this component here is a differential function. And another example would be in heat transfer, where the Fourier's heat law, you are going to learn this in your second year later on. The rate of heat transfer Q, we denote this by Q, is actually equals to negative K. So K here is the thermal conductivity times A times the gradient of temperature according to the x-axis. So this part here is actually the differential component. So since we have this is just two examples of differential equation in chemical engineering, actually we have more than that. We actually have Fick's law, we actually have reaction rate and so on. So this equation, we will see that from this equation there are unknowns function and its derivative. So this is derivative, the differential component. These two equations are actually called differential equations since it has the differential component or the derivative, and the quantity that being differentiated is called dependent variable. So for example, in equation 1 here, V here is actually the dependent variable. So V here is the dependent variable. Similarly with T. While the quantity with respect to which the dependent variable is differentiated is called as independent variable. So this would be independent variable. Similarly with X here. So if the function involves only one independent variables, in this case, equation 1 and equations 2. So since in these particular cases, you will see that for these two equation, for these two differential equation, we only have one independent variable. So if we only have one, therefore we're going to call it as ordinary differential equation or ODE. However, if we have more than two equals two or more independent variables, for example, if we have dt del t over del x plus del t over del y equals to, for example, q in the direction of xy. So in this particular equation, you will see that we only have one dependent variables, which is T, temperature. However, we have two independent variables. So since we have two independent variables, therefore, this is a PDE, or partial differential equation. So if you try to compare between, so we denote this as equation 3. So if you try to compare equation 1, 2, and 3, you will see that in addition to the number of independent variable, you will also see that the symbol for the differentiation is also different. This is due to the fact that if we have one independent variables, therefore we're going to differentiate the dependent variables only to one component. So that's why we use dv over dt. However, if you refer back to equation 3, you will see that each of the component of T, the component of temperature, is partially differentiated to two components, which is namely X and Y. So that's why we have del here. So del here indicates that it's actually a partial differential equation, meaning that we have more than 2 or equals to the number of independent variables that being differentiated against. So this is PDE, partial differential equation. And if you refer back to the example of the example of differential equation that we have, it's actually classified according to order. So this is just a recap of what we have covered in the previous slide. So before I go to the classification of differential equation, I would like to show an example of ODE in chemical reaction problem. So for example, if we have a chemical reaction of the type of A plus B is equals to C. So if we add these two substances together, we will get C. However, we have a reversible reaction here, and this reaction actually takes place in a reactor where the material balance can be applied as this. So we have input output plus accumulation. If you refer back to the reactor here, so whatever that added the reactor and generated inside the reactor is actually equals to the output. So the output plus the accumulated inside the reactor. So for batch reactor, sorry about that. For batch reactor, generation and also accumulation is equals to 0. So what we're going to see would be input is equals to output. So this is for batch reactor. So if we try to do a material balance or mass balance of that particular reactor, we will see that we will get a 3 ODE, 3 ordinary differential equation, where we're going to see the rate of change of substance A with respect to temperature, time. So this is the rate of change of reactant A, the rate of change of reactant B, and the rate of change of reactant C. So if we try to, you may refer to your notes in your CPP1, if I'm not mistaken, and if you refer to that particular notes, you will see that it's actually an ODE equation, ordinary differential equation, due to the fact that the rate of change only depends on one independent variable. So ODE are classified according to their order and their linearity. So the order of ODE is actually the order of the highest derivative present in that equation. So for example, in this particular equation, the first equation, we will see it is actually a first order due to the fact that derivative here is in the first order, while if we look at the second equation, we will see that the highest derivative is actually in the second order. And if we look at the third equation, the highest derivative is actually in the third order. So this is the classification of ODE according to its order. Another classification of ODE is according to its linearity, whether it's linear or non-linear ODE. So if we refer back to this particular equation, we will see that an ODE is non-linear if it contains the product of the dependent variables or its derivatives or both. So if we refer back to the first equation, we will see that this is a non-linear since it does not contains the product of the it does not contain the product of the dependent variables, while the second and also the third equation are actually non-linear due to the fact it contains product of the dependent variables. So here, if we refer back, the dependent variables is actually y. So y here is the dependent variables. I'm not really sure what happened here. So as you can see that in this particular equation, in equation 2, we have y, which is the product of the dependent variables. So this is non-linear. If we refer back to the equation 3, we also see is actually the product of its derivative. So it's derivative to the power of 2. So this makes this particular equation 3 as non-linear. So this is the first one would be linear, non-linear, and non-linear. I wouldn't ask you about this classification. Just this is only for your for you to know that we have a classification for ODE. We also classify the degree of an ODE where it is the largest power to which the highest order derivative is raised. For example, in this particular, the first equation, the highest derivative is to the third order. So this is the highest derivative. The highest derivative is actually in the fifth order. So since it has the fifth order, therefore it has a degree of 5. For the second equation, we will see that the highest derivative here is actually this. However, the highest derivative has the second order, so which means that it has a degree of 2. So this is how we classify the degree of ODE according to its highest order derivative. So in our course, we are going to solve ODE in the forms of dy over dx equals to function of x and y. And if we solve it in the form of this, we actually show that it follow the Runge-Kutta method. Runge-Kutta methods. Sorry, I'm not really sure what happened here. The method has the general form of new value equals to all value plus slope times step size. So this is the general form of a Runge-Kutta equation. So if we try to write it in mathematical forms, it would be y subscript I plus 1, which is the future value of y, is equals to y I, the old value, y subscript I, plus phi. Phi here is the slope times h. So h here is the step size. So here you will see that for this would be the general form of Runge-Kutta equation or Runge-Kutta method. So this would be, we call as general form. So slope here, the phi here is actually used to extrapolate from an old value yi to a new value over a distance. So this is the slope. I'm sorry, I think I need to check why does the slide keep moving. So just I think I need to write that again. So this is the general form of Runge-Kutta equation. So if we try to draw it on a graph, so for example, if we have a function that we wanted to integrate, so this function is from x, so the interval is I plus 1. So this would be the interval. And then this is yi and yi plus 1. So if we refer back to this equation is actually a linear form of equation. So we will see that slope, the estimate of the slope here. I just put different color. The slope that we estimated here, which we refer as phi, is used to extrapolate from an old value of y subscript I, to a new value. So we are going to of yi plus 1 to get this. So over a distance of h. So this would be h. So this is how we represent the general form of Runge-Kutta methods in terms of graphical representation. So you will see that later on, you will see that all Runge-Kutta's method, the same generic form. Then the only difference from these methods would be how we are going to evaluate the value of phi, which is the slope. So we are going to start with the easiest method. So the easiest method, so here, before we go to the easiest method, I'm going to brief you in this particular course, we are going to learn not four mains, but more than four, Runge-Kutter's method. So the first one would be the easiest one, which is the Euler's method, followed by Heun's method, midpoint method, and also higher order Runge-Kutter's method. So in terms of accuracy, the least accurate would be Euler's method, followed by Heun's method, midpoint methods, and the most accurate one would be the higher order Runge-Kutter method. So this is accuracy increases. Why do we have this situation or phenomenon? The reason why is that the way that we evaluate the slope. So if we refer to the first method, the way that we evaluate the slope is by using the initial slope. So if we refer back to the one that I shown you, the graph here, the slope that evaluated by Euler's method is only at the beginning or at the initial of the function. However, this is actually not really accurate, as we know that this is, let's say that this is the function. So this is the real function. If we try to assume that we are going to use the slope, the slope that we evaluated at the initial point, we will overestimate the value of yi plus 1 due to the fact that we extrapolate linearly. So what happened is that the accuracy, we still have, this is the error here. So as you can see that if we do differentiation or using Euler's method, the accuracy would be the least accurate compared to the Heun's method, Midpoint's method, and so on. So for the first one, this is just a repetition of what we have mentioned, where Runge-Kutter's methods solve ordinary differential equation in this form, and then this is the general form of ODE or Runge-Kutter's method. So this is Euler's method. So Euler's method, it's named after Leonhard Euler. So this Leonhard Euler was a Swiss mathematician and also physicist. He introduced several mathematical notations such as function x, Euler's number, summation, and I, the imaginary number. And he also had introduced Euler's method to solve ordinary differential equation. And it's actually the simplest method to solve an ODE with a given initial value. So just to introduce you to this particular person, this person, if I'm not mistaken, if you read his biography, he has his eyes is actually blind in one side, if I'm not mistaken, and at the end of his life, he's actually completely blind. But during that time, where he has a partial vision, he actually has produced more than 100 publications, which is quite impressive. So if you see, I'm not really sure if you watch this TV series. If you watch The Big Bang Theory, one of the character is Leonard. So Leonard here is named after Leonard Euler. So this is which is also a mathematician and also a physicist. So this is just introduction on Euler, on Professor Euler. And Euler's method is where we are going to use the first derivative to provide a direct estimate of the slope at xi. So what happened is that the first derivative provides a direct slope. So this is the slope here. So this is phi. So phi here that provides a direct estimate of the slope at x subscript I, and f xi here is actually the slope, is the ODE evaluated at xi and also yi. So if we substitute this equation into the general form, so if we refer back to the general form of Runge-Kuta's method, so this would be the, so if we try to substitute 1 into this general form, we will get equation 2. So the only difference here would be the slope. And this is known as Euler's or Euler's-Cauchy method, where a new value y is predicted. So we are going to predict the new value of y using the slope. We extrapolate linearly over a step size of h to get the value of yi plus 1, or the future value. So as you can see that this is, if we integrate it analytically, this would be the value, the true value. However, if we try to extrapolate the value using Euler's equation, we will see that we're going to have an error here. So this would be the error. And as you can see that the error is quite big, and this is why we don't really use Euler's equation in order for you to do mathematical or engineering problem later on. But it's a good method to start with, actually. So I'm just if we refer back to the example, so this is the example for Euler's method. So for example 1, we are going to use Euler's method to numerically integrate this function here from x to x0 to x equals to 4 with a step size of 0.5, and the initial condition at x equals to 0 is y equals to 1. I'll just delete this one. So it would be, so this would be equation 1. And then remember that we wanted to keep to 6 significant digits only. And from the question itself, we are going to differentiate between this interval, x equals to 0 until x equals to 4, with the step size of 0.5. And it also says that when x is equals to 0, y is equals to 1. So this would be the statement for this particular equation. So what does it mean actually? For example, if we try to draw this on a graph. So this is 0 to 4. I'm not really sure how the function would be, but I just try to, so it would be something like this. So it's not supposed to be a linear line, but just a linear equation, but I just put it for the sake of this graphical representation. So it says that we are going to differentiate the function from 0 to 4, where we are going to differentiate it with a step size of 0.5. So we are going to every 0.5, and so on. We are going to get the value of yi plus 1. And at the end, we are going to see what is the value of yi plus 1 at xi plus 1 equals to 4. So this would be the value that we wanted to get. So before that, we need to draw a table. So this is x and y Euler. So x here is 0, 0.5, 1, 1.5, 2, 2.5, 3, 3.5, and 4. Oops, I don't know what. So let's say that this is y Euler. Okay, so it's a bit hard for me to. Okay, so this is from 0 until 4. So first it says that at x equals to 0, the value of y is actually 1. So we are going to assume that this function here is y. So this is actually y prime. However, we are going to assume that this is y. So if we try to find the value of y Euler's, if you try to get this value here, this is actually 1. And the second step is 0.5 due to the fact that h is actually 0.5. So what we are going to do is to start with 0.5. So at x equals to 0.5, so remember that we have for Euler's, we have the equation as this. So this would be the equation for Euler's, and then we are going to fill in. So since we wanted to find the value of y at 0.5, and then the previous all value is 0 plus the all value is 0, and at x equals to 0, y is equals to 1, and h here is 0.5. So we need to find this. So if we try to do this on the side, so we substitute, what happened is that in this particular, because I don't want you to get confused, for this line here, this means that you need to substitute x equals to 0 and y is equals to 1 into this equation. So we just denote this as 1. So if we try to substitute x equals to 0 and y equals to 1 into 1, we will get this equation, this value. So we just substitute 0, 3 plus 12, negative 20, 0 plus 8.5. So we directly know it's 8.5. Just cancel out. So we only get 8.5. So if we substitute, so it says that y at the value of y at x equals to 0 is actually 1. We add 1. This is the value here. Plus the function at x equals to 0, y is equals to 1. So we just already solved this here. 8.5 times 0.5. So we will get around 5.25000. So this is 6 significant digit. So this is for x equals to 0.5. And then we need to do at 1. So we just follow this equation. So the previous is 0.5 and 5.25. H. So if we try to substitute into equation 1, we will get negative 2, 0.5 to the power of 3 plus 12 to the power of negative, power of 2, 20, 0.5 plus 8.5. So we need to calculate that. So if we try to substitute everything, 5.25 plus the value here that we get, times 0.5, we will get around 5.8750. So this is for x equals to 1. And then we're going to add to continue with 1.5. So since we have we only have 10 more minutes, I hope that you can try to do this yourself at home. So this would be 2, 2.5, 3, 3.5, and 4. So you need to get the value of the Euler's number. In fact, I think I'm going to give you the value here so that you can check with whatever value that you get. So you will get something like this. So I presume that you are going to do this during after the class at home. So as you can see that we actually can calculate the value from x equals to 0 until x equals to 4.0. And then since I mentioned in the previous slides that Euler's method actually has the least accuracy of all Runge-Kutter's method. There are two types of error that we can actually get from the Runge-Kutter's method, not only Euler's. The first one would be truncation or decretization errors, where it is caused by the nature of techniques employed to approximate the value of y. So this is how we estimate the value of the slope. As I mentioned before, since Euler's method, we only use the initial slope to extrapolate the value of the future y. Therefore, the accuracy of Euler's method is much more, is the least of all Runge-Kutter's method. So this is this fall under the truncation errors. And also another error would be the round-off error caused by the limited number of significant digits. However, in this particular course, you need to keep in mind that in order for you to minimize this error, please try to keep your significant digits to 6. Your answers to 6 significant digits. So there are two types of errors. The first would be truncation errors. So these truncation errors we can minimize by choosing a method that's more accurate compared to the other methods. And the second method would be the round-off method error, where we actually can minimize this by using a more higher significant digits. However, in this course, we are going to fix to six significant digits only. So this would be the truncation error. So truncation error that result from application of the method in question over a single step. So Euler's method is actually one single step, and propagated truncation error results from the approximation produced during the previous step. So for example, if we refer to this table, in order for us to get this value, we need to use the previous value that we get. However, if let's say that we already obtain a wrong value here, the value in the subsequent step will also be propagated to a larger inaccuracy. So that's why we say that it's a propagated. It's caused by a very small error in the first step, but then it accentuated or become bigger as it moves in the next step. Because in numerical differentiation, we are using the old value to get the new value. So if the old value that we got, that we use are wrong, therefore the subsequent step will have also wrong values. And these wrong values will actually propagate it. So in order for us to ensure that we have ensure, in order for us to ensure that we have not least a more accurate, we need to make sure that the approximation that we use in the previous step are the correct one. So the total error would be the local truncation error and also the propagated truncation error. So how do we calculate this? So for example, if we refer to equation to example number 1. So example number 1, it gives us the value of dy dx as negative 2x. So this would be to integrate from x 0 to x equals to 4 with h equals to 0.5. In order for us to know the global truncation error, if we try to do this analytically, solve it analytically, we can get the exact solution as y is equals to negative 0.5x to the power of 4 . So how do we calculate the global error? So the global error is actually the value that we get. So global error is actually the modulus of the y value that we get from Euler's minus the y value that we substitute. For example, if we wanted to get the value of, if we try to do table, so this is x equals to 0, 1, y Euler, and y true. So y Euler is using equation 1 and y true is using equation 2. So y Euler 1. And for the second one, if we refer back to the example here, it's actually 5.25. And in order for us to get the y true value, we just substitute 1 into equation 2. So if we try to substitute 1 into equation 2, we will get 3.21875. So that would be the value of the exact solution, the y value that we get from the exact solution. So in order for us to get the global error, it's actually modulus y Euler's minus y true over y true. So if we use this particular value for x equals to 1, so global error at x equals to 1 is actually y Euler minus 3.21875 divided by 3.21875, 100%, equals to 63.1%. So this is a global error for each step. So how do we decrease the value of the global error? So the global error actually can be reduced by decreasing the value of h. And the method will actually provide error-free prediction if the underlying function is linear. So previously we used h is equals to 0.5. However, if we decrease the value of h to 0.1, what happens is that the global error will also reduce. So global error, I just will also reduce. Another way on how you can reduce the global error would be if we have the underlying function is linear. So what does it mean by linear? If the solution of the differential equation is linear, because as you can see that if we have a straight line, therefore, so if we try to do, so if let's say the function is linear, therefore if we try to use Euler's method, since Euler's method use a linear extrapolation, therefore what we get would be at the exact value of the y Euler's and also the y true value due to the fact that we have a linear function. But that's very rare in our engineering field. So I think I'm going to stop now. We actually have several methods, but I think I'm going to discuss these methods on Friday, hopefully, or next week. So I think that's it for now. Any question? Any question, class? No?